Okay, this is the additional video on partly some stuff you've already done, so I will just do a little bit of revision, but we're going to look at the equation. The main idea of today's lesson is to look at the equation which is written here, that F equals BIL. You might not know what some of these mean yet, but we'll come to it. So what we're basically going to do is describe what happens when current carrying wires and magnets interact. You've probably seen that already. Be able to revise something called the left-hand rule, and then we're going to get to the main equation, okay, which F equals BIL. So first up, let's just hope you remember this. This is the left-hand rule. The thumb is the force or the motion. The first finger is the direction of the magnetic field from north to south, and the second finger is the direction of the current. And this is current, assuming it flows from positive to negative. This is Fleming's left-hand rule. You need to sort of know about it in order to understand the motor or the motor effect, and in today's lesson to understand this equation. Okay, so hopefully you've seen that in a previous video, but I just wanted to remind you of it. Okay, so we can use this, the idea of the left-hand rule, and look at an experiment like this. And if we put a wire between two magnets, so this is a wire between two magnets and it's connected to a battery, so we've got electricity flowing through a magnetic field, and you can see that they're perpendicular, so that means the direction of the current is at 90 degrees to the direction of the field, and what we get a force. Okay, so the size of this arrow is indicating the direction and the strength of the force. So if we increase the number of batteries, then with two batteries we're going to get a greater force than with one battery. Okay, if we increase the size of the magnet, so if we have a larger magnet, we'll have a larger force. And the one that's harder to understand is if we increase the length of the wire that goes in the magnetic field. So if I click this here, you can imagine sort of running wires next to each other in parallel. Then that's the longer length of wire. We'd have a force on all of the wires, so therefore we'd have a larger force. So just to recap, a larger current gives us a larger force. A larger magnet, now not necessarily a larger magnet, but you'd say a stronger magnet gives us a larger force, and more wire actually in the magnetic field, so a longer length of wire would also give you a larger force. Now, in terms of an experiment you may have done at school, it's all very well looking at an animation, but you can set up an experiment like this, where you have a top pan balance, which measures effectively how much mass is on top of it, and what it's really doing is looking at the weight of the object on top of it, and then you've got a wire passing through it, and the thing that's on top of it is a magnet. So this magnet would be a north and a south pole, so you'd have a magnetic field going between these two magnets. You'd have a wire going through it, and then you'd connect that wire to a power supply. Now with this, because you've got a current flowing in a magnetic field, you would experience a force. And the thing that you need to remember here is that if the magnet, I'm going to use Newton's third here, if the magnet puts a force on this wire, then the wire puts a force on the magnet equal to it and in the opposite direction. So if this wire was moving upwards or forced upwards, then the magnets would be forced downwards. So what you'd get on this reading here, you'd get an increase in the mass, because it was as if it would be as if the magnet is pushing down on the top pan balance even more. So you might get some results like this. With no current flowing, the mass would be 1.65 grams. I've converted it to kilograms, 0.00165, and that means if I multiply that by 10 to give me a force in newtons, that will give me a force of 0.0165. Now, as you can see from my demo results there, if I increase the current, then the mass reading is increasing, and that must mean the wire's being forced upwards, so the magnet's being forced downwards. And each of these, an increase of 1 amp to 1 amp and another amp to 2 amp, is giving us an increase here of a force of 0.0165 to 0.169 to 0.173. So you can see hopefully that an experiment that would prove this idea that the last animation showed. And what you could do with this experiment, you could increase the strength of the magnets, and if you increase the strength of the magnets, you would also see that that would increase the strength of the force, and you could increase the length of the wire, and if you did that, you would also see that that increases the size of the force. So what you do, you'd have to come up with an equation. This is the equation that you do need to know for this. In fact, I think this one's on the formula sheet for the AQA specification, and this is here. What we're saying is that force is proportional, this symbol means proportional, force is proportional to the current, force would be proportional to the length of wire, and force is proportional to B. Now B here is the magnetic field, okay, so this symbol means proportional, and this B is the magnetic field strength. It's actually something called flux density, and it's measured in a new unit which you need to know, which is the Tesla. So the Tesla is the unit for magnetic field strength, and what you've hopefully got from the last diagram, the last experiment, is that force is proportional the current to the current, the length, and the magnetic field strength. So what we would say is that F is equal to B, the magnetic field strength, multiplied by I, the current, multiplied by L, the length. All right, and this equation you are given, so you don't have to learn it, but it is something that you do need to be able to use, and especially understand that B is measured in something called Teslas, and it's a measure of the strength of the magnetic field. Okay, so you don't have to learn it, just to say. So a very quick example: a 30 centimeters length of wire carrying 2.6 amps sits inside a magnetic field. The current flows at 90 degrees to the direction of the field. It experiences a force of 0.14 newtons from the motor effect. Calculate the magnetic flux density of the magnet. So if we put our formula up here, F equals BIL. I did forget to say, sorry, force must be in newtons, current must be in amps, and the length must be in meters. So we've got F equals BIL. Let's put some numbers into it. So 0.14 newtons is equal to B. We need to find it, multiplied by 2.6 amps, multiplied by 0.3 meters. I've converted 30 centimeters into meters to give me 0.3. Then it's just a matter of solving this. I can say 0.14 equals B times 0.78, multiplied by those numbers, and then B must be equal to 0.14 divided by 0.78, which, if you use your calculator, is 0.18 Tesla. Okay, so that's our first one. Quite a difficult one because we've done a conversion of units and also a rearrange of the equation. So just a couple more. One of these might be slightly easier. A wire is at right angles to a uniform magnetic field of flux density 0.05 Tesla. 0.2 meters of the wire is inside the length of the field. If the current is 6 amps, what's the force and in which direction? So using F equals BIL, 0.05 Tesla times 6 amps times 0.2 meters gives us a force of 0.06 newtons, and we would say that it is at right angles to the wire and to the field. That's the direction of the force if you think back to Fleming's left-hand rule. The last question: a wire lies at right angles to a magnetic field of flux density 0.1 Tesla. 0.5 meters of the wire is inside the length of the magnetic field. If the force on this length of the wire due to this current is 0.8 newtons downwards, what is the magnitude of the current in the wire? So using our formula, F equals BIL, let's put in what we know. It's definitely 0.8 newtons. The magnetic field strength is 0.1 Tesla. We don't know the current, so I've left that as I, and the length of the wire is 0.5 meters. So doing some maths, 0.1 times 0.5 is 0.05, so 0.8 equals I times 0.05. I therefore is 0.8 divided by 0.05, just rearrange the equation, and that gives us a current of 16 amps.